All right, thanks everyone for joining me in this linear algebra course. I love linear algebra, I really do. It was my favorite undergraduate class because to me it was something that was different than calculus, and I could really start to see how mathematics could be used in the real world. And I really like teaching it because I like exposing students to those very concepts, new mathematics that can really be used. It's a broadly applicable subject that's really the foundation of a lot of higher mathematics, and so I'm excited to be in this course with you, even remotely. I'm going to start out today by just doing a brief introduction, followed by section 1.1. And something you'll find in this video, but also in subsequent videos, is I'll often stop at certain times. And when I teach this in class, I usually stop and ask people to work on problems or look for responses from the class. And I'm going to do the same thing in this remote setting. I'm going to sort of stop and ask people to think about something or pause the video and try a problem before looking at the solution. And I really strongly recommend you do those things. Just like in a real class, I obviously can't force anyone to do anything. But those are the kind of things that really help you understand the subject and dig your teeth in, so to speak, to see how well you understand things, and really just engage your mind in the subject. So I strongly encourage you to do that as we go here. So this first introduction section is just sort of talking about what is a linear equation and sort of reminding us about how we solve them so that we can build into the more applicable topic of linear algebra. So the first thing I'll just note here is we're going to talk about what is a linear equation. And the first thing to note is that when we talk about linear equations, usually in calculus and previous classes we use variables x, y, and z when we're talking about math. But in this class, we're going to talk about more than just one or two dimensions, which we oftentimes talk about in other classes. And so instead of doing x, y, and z, we usually start labeling just x's with subscripts, so x1, x2, x3, because we may want to have lots and lots of different variables. And so just keep that in mind. We're not doing x, y, and z anymore. We're doing x1, x2, x3, and those are going to be the variables in the equation. So this is your very first chance to sort of pause the video and think about something for a second. So think about something, what is a linear equation and what is a nonlinear equation? What does that mean? And as you think about that, you should think about the word linear, right? So you should be thinking about linear means line, straight line. Think about what the equation of a line looks like and what are sort of the characteristics of a line. And maybe to help you think about that in terms of nonlinear, what does a not straight line look like? And what are characteristics of something that would not create a straight line? And so again, I would just encourage you to pause the video right now and just think about that. Maybe try to write down, if this is in person, I usually have people group up and sort of talk to their neighbors about something that's linear and nonlinear. And I would just encourage you just to take a second and think for yourself, what does linear and nonlinear mean? And I'm obviously going to go over them in just a second here. And so I will write sort of the definition down of what linear is, and I will write the definition down about what nonlinear is. And then we'll look at some examples of those. And again, if you have paused the video, that's great. You should unpause it, and we'll go over that answer now. So what you should be thinking about for linear is kind of like the equation y equals mx plus b, right? That's usually what people think of when they think of straight lines. But here, instead of y equals mx plus b, we're going to use x1, x2. So we'll say x2 equals m times x1 plus b, right? So this is your first sort of example of a situation where we're not using y's anymore, right? We're just labeling the variables with x's. So this is the y equals mx plus b form. In this particular equation, m and b would be real numbers, right? So if you remember your straight lines, m tells us the slope, b tells us the intercept, and then x1 and x2 would be the input and output, right? The variables there. But the key thing to sort of keep in mind when we look at this equation and when we write down the definition about what linear is that the variables x1 and x2 in that equation have powers of 1, right? So when we think about a linear equation, all the variables should have a power of 1. And visually speaking, that means they make straight lines. looks like a straight line if we have two variables. Or if we're in higher dimensions, it looks like a plane. So think about a piece of paper. And so, for example, a linear equation in a higher dimension might look like this. Let's say, let me get another color here so we can break it up a little bit. Maybe x1 minus 3x2 plus 4x3 equals 7, for example. That's also a linear equation in three variables, right? We have x1, x2, x3 in that second equation. But the point is, all the powers of those variables are 1, and so that's what makes it linear. And we can have lots and lots and lots of variables in an equation, and it could still be linear. So I'm just going to write a sort of a longer one down that has 6 variables. It's a linear equation because all the powers have 1, and it's obviously an equation because it has an equal sign, right? And so this is a higher dimensional linear equation that we can't really visualize. We couldn't sort of draw that because it's in higher dimensions. But if we could draw it, like this one, for example, x1 minus 3x2 plus 4x3 equals 7, that is something we could actually draw because it has 3 dimensions. That would look like a piece of paper going through space. So the linear part just means it makes straight, the output is either in a straight line or on a plane. And so with that in mind, hopefully you're thinking that nonlinear means that variables have a power other than 1. So any nonlinear equation would have a variable that have powers other than 1. And so visually speaking, that makes a curved graph. Right? A non-linear graph makes something that's not a line, right? Non-linear means not linear. So with that in mind, we could easily think of some non-linear equations, right? So like y equals x squared or something. In this case, we'll do x2 equals 3x1 squared, right? So the squared part here is what's making this non-linear, and we know that that makes like a U-shaped kind of graph, right? But it doesn't have to be powers necessarily bigger than 1, right? So they could also be fractional powers. So something like x2 equals square root of x1 is nonlinear because we could think about that power as a power of 1/2, right? Square root has a power of 1/2, and so that's also a nonlinear equation. And there's lots of different sort of examples like that we could come up with that are nonlinear, just to sort of throw a couple out there that don't quite fit into this powers other than 1 box. Sine, right? That's nonlinear. We know that sine makes like a wave kind of shape, right? Which is obviously not a linear shape. And so that's nonlinear. And logs and exponentials are also nonlinear for that matter as well. So something like log of x or e to the x are nonlinear. Again, the powers of 1 don't really fit nicely into that sort of definition, but we can certainly tell that those are curved graphs, right? If you remember what the graphs of logs and exponentials looks like, they're curved. So the reason that I'm talking about this is that in linear algebra, we're talking about linear equations, right? So in linear algebra, we're talking about linear equations, and so things will always have a power of 1. Now, there might be lots of variables, and there might be sort of several equations, but all the powers are going to be 1. That's sort of the key thing to point out right now. And moreover, the thing that we're really interested in are systems of linear equations, right? So in this class, we usually discuss systems of linear equations, which are 2 or more linear equations that share the same variable. So, for example, I'm going to write down a linear system, and I'm going to sort of bracket them in with a curly bracket that sort of shows that they go together. So something like 2x1 plus 4x2 plus 8x4 equals 7, x1 minus 3x3 plus 6x4 equals 0. That's a system of linear equations because there's more than one linear equation, right? Each one has a power of 1. Each variable in its respective equation has a power of 1, and there's 2 of them. So we would say that this is a system of 2 linear equations, right? Because there are 2 of them. And I'm going to write a second one down right here. in 4 variables, because there are 4 variables, right? x1, x2, x3, x4. So just some vocab for you, so when you hear someone say something like, oh, that's a system of 2 linear equations and 4 unknowns, or 4 variables, you know that means, oh, there's 2 equations and there's 4 variables. This is another opportunity for you to pause the video and give something a try, and I would strongly recommend you do that. It really is the best way to learn. And what I usually ask people to do is write down a linear system of 3 equations in 2 variables. And again, you should use x1, x2 for the variables, right? So just take a second, pause the video, see if you can write down a system of equation that has 3 equations and 2 variables. Lots of different answers could fit into that box. And one that I'm going to come up with right now is this. 5x1 minus x2 equals 3. x1 plus x2 equals minus 1. 7x1 minus 4x2 equals, say, pi or something. Right? So there's 3 equations there. Each equation is linear itself because they are powers of 1, and there are 3 of them, right? So 3 equations and 2 unknowns. Okay. So now that we kind of have an idea of what linear equations are, I usually like to just start off by also mentioning where this stuff is applied. And we don't do a ton of applications in this class, to be perfectly honest with you. It's a math class where as I mentioned, it's a foundation for lots of higher math, and so we're trying to sort of cover a lot of material, and I just don't do a ton of applications, to be honest. But there is a section later in the course where we do focus on just applications, and I'd just like to usually touch on that section right now, just to give people a little bit of a preview of how this stuff might be used. So this is from section 1.6. You can see that it says that right at the top of the page, right? It's from section 1.6. And so we will see this again later in the course in section 1.6. But let me just sort of give you an idea of a couple examples of where this is used. Again, very widely used, and that's why oftentimes in this course, people from lots of different disciplines end up in here. So not just math people, but physicists and computer scientists and engineers and lots of people who have quantitative majors and jobs have to take linear algebra. It's just a huge part of lots of courses. So anyway, here's a quick example of how it can possibly be used in an economy type setting. So in this particular economy, and I'm just going to briefly go through this, we go into this more detail in section 1.6, but there's 3 parts of the economy here. We have coal, electric, and steel. And what we're trying to do in this particular problem, and you can see it says right here, like it's sort of talking about how the consumption and output of each one of these sectors, which is summarized in this table. And so what this basically says is coal purchases 60% steel, 40% electric, 0% coal to run its business. The electric industry uses 20% steel, 10% electric, and 60% coal to run its business. That's sort of what this is saying. And if you think about these sectors as being represented by these variables, so PC is coal, PE is electricity, PS is steel, we can find equilibrium prices that make the income match its expenditure. In other words, if whatever coal is producing needs to be bought, ideally, and whatever electric is producing needs to be purchased, and whatever steel is producing needs to be purchased, and they need to be purchased by each other industry because they use each other to run each other's industry. And so, again, we'll look at this more closely later, but this table, which tells us how things are produced and bought in this sort of hypothetical economy, is summarized or can be translated to, so this table can be translated to this system of equations. And so you can see, like, the first row is the first equation, right? So coal purchases 60% steel, 40% electric, no coal, right? That's what this says right here. And just to be clear, there's like a 0 coal there, right? And so right off the bat, we see we have a system. It's a system version of the table. It's a system of linear equations, right? So we have linear equations here because all the powers are 1. And then what we often do if we create a system like that is we rewrite it when we get all the variables over to one side. So from here to here, this is just rewriting the same system. It's just rewritten, where we have the variables on one side, and then an equal sign, and then we have the constants over on the right. And so that's something we'll see quite a bit, is we usually keep the variables on one side. That lets us translate it into a matrix, which is what linear algebra is all about. And then we have the constants on the other side, which are going to end up being solutions. And so what we're going to see pretty soon is we can solve this thing using a matrix. So I haven't said that yet, but linear algebra is a study of matrices and matrix manipulation to solve systems. And this is sort of your first introduction to how we can take a real-world problem, make a system of linear equations, and then we'll see that we can put that into a matrix and solve. And we will actually solve this problem in section 1.6. Another just sort of quick example that I like to do, just preview, is this chemical equations one. So this is an example from chemistry. Chemists often, forget to mention that before, chemistry, linear equations, or linear algebra, excuse me, is really big in advanced chemistry as well. So if anyone's a chemist, this might be of interest to you. But the idea is we have this conservation, we have lots of conservation laws, but this one is the conservation of, I think it's conservation of mass, if I'm not mistaken. And so this is a situation where we're talking about burning propane, right? So we're going to have propane gas, which is represented by C3H8. And when you burn propane, so think about like lighting your grill or something like that, your propane grill, propane combines with oxygen, O2, to form carbon dioxide and water. That's the byproduct of burning propane. And so that can be sort of represented by this balanced chemical equation, right? So here is propane and oxygen mixing together, right, when you burn propane, and what's produced, which is the arrow here, is some amount of carbon dioxide and water. Now, the variables in here, the x1, the x2, the x3, the x4, those are linear because their powers of 1, and we can see that we need them to be equal on both sides, right? In other words, when you burn propane, the propane and matter in general is not destroyed, and so the propane and the oxygen on the left side need to somehow transform into the things on the right and have the same amount on both sides of the equation, right? You can't like lose oxygen somehow when you burn propane or carbon or any of the other things. And so we can take this balanced chemical equation, again, we'll look at this in more detail in 1.6, but it becomes this vector version right here. And so this is your first introduction to what maybe vectors look like. We'll see vectors quite a bit. And so we see that like carbon dioxide has 3 carbons and 8 oxygens. And so that's being represented by 380, right? So in other words, the first row in these is the carbon, the second row is the hydrogen, and the third row is the oxygens. For example, H2O has 2 hydrogens and 1 oxygen, right? H2O, no carbons. And so this is sort of the vector version. And if we want to balance this equation, we need the amount on the left to equal the amount on the right, right? And so we can take this vector version and translate it into this mathematical linear system. So this is now a linear system created from the previous concept. It's also known as a vector equation. We'll see that vocab pretty soon. And we see that we're trying to balance both sides, right? So this is the carbon dioxide and the oxygen mixing, and it needs to equal whatever is produced in terms of carbon dioxide and water. And so the x1, the x2, the x3, and the x4 are the amounts of each one of those things, and we need to try to balance that equation, which just comes down to solving the system. Again, we'll see that more in section 1.6, but basically what you end up doing here, trying to do that here, is this vector equation becomes this linear system. Right, so like let's just look at the first line, 3x1 equals x3. If we look at the top row here, that's exactly what it says, right? 3x1, no x2s, no x4s, just equals x3, right? So this first line, or this first equation is the first line of that vector equation. And so this becomes a linear system, and just like on the last page, we can subtract all the variables over to one side to get this version, right? So this is just rewritten just like we did on the last page as variables equals constants. And solving this linear system would allow us to balance that chemical equation. In other words, it would tell us how many, given a certain amount of propane and oxygen that are used, how much carbon dioxide and water are produced. Again, we'll solve that later. Actually, it might be a homework problem. Oh, no, it is an in-class problem to solve that. And we will take a look at that in section 1.6. All right, so that's the end of my sort of introduction. I hope you've sort of an understanding now of what a linear equation is, and a few examples of where we might see them in the real world. And then the next section, section 1.1, is going to start by talking about what we do with linear equations and how we think about solving that system. And just to be clear, the entire first chapter is all about creating matrices and solving them, and then we sort of get more complicated in the subsequent chapters as we move through that.